right, topic 5, logarithmic regression. Hopefully, this will feel familiar because you've done regression so many times before. Just to let you know, on page 66 of your booklet, there are the calculator steps for regression. So keep that in mind. Keep that handy. I'm actually going to just pull it out because it never hurts to have it handy. So if I need to refer to it, actually I'm getting pretty good at it now. Mwah. Anyways, so as we've learned before, a scatter plot is a set of points on a grid used to visualize a possible trend in the data. A logarithmic regression function is the equation of a curve of best fit when scatter plots look like a logarithmic function. Technology uses logarithmic regression to determine the equation that balances the points in the scatter plot on both sides of the curve. This sounds very familiar, doesn't it? Now, our general form of the logarithmic function is y is equal to a log bx. The calculator, however, generates the regression equation using natural logs, resulting in the formula of the following form. Y is equal to a plus b ln x. Okay? Alrighty. Example. Using a logarithmic regression to solve a problem. Lydia is researching the rise in tuition fees for post-secondary education in Alberta. She found some data that used tuition fees in 1992 as the benchmark, assigning them a value of 100%. The tuition fees in all other years compared with the tuition fees in 1992. Okay, so they're a percentage of that value. So we are going to set this up. So this will be our L1 and this will be our L2. Okay, so we're going to set up this data in our function. Okay, so we're setting it up where the year is a function of the percentage of the tuition fees. Okay, so it's a little bit backwards there. So the year will be Y, and the tuition fees will be X. So that's why we have L1 as the tuition fees and the year as X. So let's put these in. We're going to edit. So it's stat, and then we select 1, enter. So we're just going to put these in. 37.8, enter. 43.8, enter. 54, enter. 58.8, 69.4, 100, 222.7, just popping in these values, 287.1, and 305.9. Quick glance, I'll double check them later. Hopefully I put them all in right. So we have 1979, and then we have 1982, 1984, 1986, oops, I missed a one. I felt it too. 1986. We just going up by 2? No. 1989, 1992, 1999, 2004, and 2006. Okay, we all match up. Everything looks okay for my numbers. All right. So we put our values in. So again, the year is a function of the tuition fees. So year would be Y and the tuition fees is X. So that's why this was L2 and this is L1. Okay. Label the scatter plot including your window settings. Okay. So let's do the scatter plot. First, we're going to make sure our stat plot is on. So 1, we're going to turn it on. We want a scatter plot. X list is L1, Y list is L2. We're going to set our windows doing zoom 9. And there we get our scatter plot. So if we can see on our drawing, it looks something like do, 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 do. We got a big gap, do, do, do. My windows, if I look at what my windows are, it went 10.99, 332.71, 1 for my X, and my Y was 1974.41. 2010.59 and 1. Okay, so those are our window settings, right? So there we go. If we label this further, we put that the year was Y value, so this is our year and this is our tuition. Okay, so that's kind of labeled really crappy. Determine the equation of logarithmic regression. So remember, it puts it in a slightly different form. So we're going to go stat, calc, right? And we want logarithmic regression. So if you look at the sheet, page 69, or 66, sorry. For logarithmic regression, we go down, it's ln reg, natural logs, right? 9. We're going to go second function 1, comma, second function 2, right? Just so we make sure we're accessing lists 1 and lists 2, and then enter. Now, see, we get this formula here, and so we get y is equal to, our A is 1937.423, that's probably enough. Plus B is 11.778. That's probably enough just for this sake. Most often than not, it's going to tell you what to round it to, right? And it says, the next question says, is it a good fit for the data explained? Well, we didn't turn diagnostic on, right? So let's redo this with diagnostic on. So if we remember how to turn our diagnostic on, we go second function 0, x to the negative 1 to get us down to the d's, and scroll down, diagnostic on, enter, enter. Now let's do that regression again. So calc. And then we are going to do our natural log regression. So that's 9. And we're going to go second function 1, comma, second function 2, enter. Now we should get our R values. So my R squared value is 0.986. So that's a pretty close to 1, right? Close to 1. So it's a pretty good fit, okay? But let's just be sure here. Well, let's see what it looks like. Let's go into y equals. Let's clear this crap out, okay? And I'm going to go vars 5 over, enter. And now I'm in there. Now I'm going to graph. And we're going to see how it fits. Now you see there's some points that don't fit exactly, but it fits actually pretty good to those points. That R squared value says close to 1, so it's not a bad fit, okay? Good way to check, right? Let's do a few more. So slightly different formula because we're doing this linear regression formula, right? So just be aware that it looks a little different. So here we have coffee is found in tea, or caffeine is found in coffee, tea, and soft drinks. Many people find that caffeine makes it difficult for them to sleep. Following data was collected in a study to determine how quickly the human body metabolizes caffeine. Each person started with 200 milligrams of caffeine in his or her bloodstream, and then the caffeine level was measured at various times. Okay, so let's start by clearing our lists. Let's go up to the top, clear, enter, go up to the top here, clear, enter. Let's also go into our Y and clear that out. Now let's go back to our stat, and we're going to enter our lists. Now it says we've got caffeine level in the bloodstream and time after ingesting. Just hold for a moment. Okay, because it is 3:15 while I'm recording this, and I'm in the school, so the bell just went. So it says, determine the equation of the logarithmic regression function for the data representing time as a function of the caffeine level. So time will be y, and the caffeine level will be x. That's how that works, because time is a function of the other one. So it's kind of the reverse, hey? So y over here, x over here. This will be our L2, and this will be our L1. Alrighty, we're going to put this data in. So 167, enter, 113, enter, 33, enter, 80, enter, 145, enter, 49, enter, 21, enter, 112, enter, 25, enter, 76, enter. And then over here, we'll put in our y values into list 2. 1.5, 5, 14, 7.5, 3, 12.5. I'll just talk about caffeine. I drink a lot of Diet Coke, you guys. Okay. Try to quit. Well, no, not really. I try to cut back. That's more accurate statement. So just glancing up at our numbers, everything looks pretty good. Yeah, okay. All right, so our data is in there. So we want to determine this equation. So we're going to do regression, right? I always like to graph it first just to make sure. So our stat plot's on. We're going to go zoom 9. And there we go. And then we're going to do our regression. So we hit stat, over to calc, and scroll down. Even if you don't remember the number, if you scroll down, you can see that you're getting a natural natural log regression, number 9. And then we go second function, 1, comma, second function, 2. Because we want to make sure we're telling it that we're looking in lists 1 and 2. And enter. Diagnostic still on. Ooh, very nice diagnostic there. So y is equal to, our a value from that is 43.79 plus negative 8.21 ln x. Okay. And again, it doesn't tell me what to round to, so I just did it to the nearest hundredth. We can put this into our y equals just to take a look at what it looks like. Enter, and look at that on the graph, see how it fits. And that will probably help us answer the next question. Determine the time it takes for an average person to metabolize 50% of the caffeine in their bloodstream. Well, 50% of 200 milligrams equals 100 milligrams, and this will be our x value. So on the graph, we're going to go second function, trace value, and we want to know for 100. So I get an answer of y equals 5.997. I can round that to 6. So approximately 6 hours to metabolize 50% of the caffeine in their bloodstream. Okay? 6.0, not 60, because it is to the nearest tenth of an hour. Okay? Alrighty. Now, this is all familiar to you. We're using these logarithmic functions to kind of answer these questions. We can answer the next one. We might be interpolating or we might be extrapolating. If we have to extrapolate, we might need to change our windows. Paula drank a cup of coffee that contained 200 milligrams of caffeine at 10 a.m. how much caffeine will be in her bloodstream 11 hours later at 9 p.m. in the morning. So y is equal to 11, because it's our time, right? So if we go, let's just double check our windows. Okay, it's in the ballpark of those numbers. So if we do here and we make y equal to 11, y2 is equal to 11, and then we graph that, then we're just going to look for the intersection, right? So second function, trace, intersect, 5. First curve, second curve, guess. So x equals 54 point, and it's to the nearest milligram, 3.5, so that would be, to the nearest milligram would just be 54. Oops. So 54 milligrams. Okay. Paula is only able to sleep if her caffeine levels are below 70 milligrams. How long will it take her body to metabolize the caffeine in her bloodstream so she can sleep to the nearest hour? So we want x to equal 70. So we want to see how long it takes for that. So second function, trace value, x equals 70, enter, and it's right there. So y is equal to 8.92, and it's to the nearest hour, so it'll be 9 hours. Okay. Using your regression equation, determine the x-intercept to the nearest tenth. Explain what the x-intercept represents in the given context. So, using this, we want to find out where y equals 0, right? Okay, because that will be our x-intercept. So let's go in here, and instead of y equaling 11, we'll make it equal 0, and we'll graph that. So graphing. Y equals 0. And I just want to double check. Yeah, it should be. So graph. Second function, trace, intersect, enter. And it's thinking, oh, goodness, maybe I don't have enough room. My y is okay. But let's expand our x. Let's go, let's just for fun, make it 250. And now we'll graph it. Because there we can really see the intersection. We couldn't really before. And then second function, enter. We want the intersection, graph 2, 3. And we're going to get for our value, x equals 207.687. So it says to the nearest 10th, so 207.7, and this means how much caffeine they started with, right? Because that's how much they have to get rid of. So I always spell caffeine wrong. I always spell it like caffeines. I don't know why they started with. So even though we thought we started with 200, they probably had a little residual caffeine in there, you know, from other sources to get to that. Okay. A logarithmic function may be a good model for a set of data if the points on a scatter plot form an increase or decreasing curve where the domain is restricted to the set of positive real numbers. So if you graph it and it looks either like this or this, then you know, oh, this is possibly a logarithmic function, right? So all my x values are positive. So doing a logarithmic regression is a way to do that. So it's the equation, a logarithmic regression function is the equation of the curve of best fit when the scatter plot looks like a logarithmic function. Now, the general form is like this. However, this is the nature of your calculator is going to do a regression using natural logs, but we can use it, okay? So remember, if you're going to be extrapolating, you might have to change your windows, okay? And you're going to really be relying on value and intersection functions once you graph it. You're also using the steps for regression that we've learned previously, but now we're finding them for logarithmic regression. All right, there we go.